To determine if the series converges or diverges, we'll be using the limit comparison test. We are given the sum from n equals 3 to infinity of the quantity n plus 3 divided by the fourth power of n plus 1. We need to begin by determining what series to compare this to. Notice if we multiplied out the denominator, the highest degree term would be n to the fourth, and therefore we can say the given series resembles the sum from n equals 3 to infinity of n divided by n to the fourth, which simplifies to the sum from n equals 3 to infinity of 1 divided by n cubed, which you should recognize converges by the p-series test with p equal 3. So again, we will say the given series resembles the series given by the sum from n equals 3 to infinity of 1 divided by n cubed, which converges by the p-series test with p equals 3, which is greater than 1. And now let's review the limit comparison test. When comparing two infinite series with formulas a sub n and b sub n, both a sub n and b sub n must be greater than 0, and if the limit as n approaches infinity of a sub n divided by b sub n exists and is equal to L, which is greater than 0, then both series converge or both series diverge. Because we are comparing to a converging series, if the limit exists and is equal to L, which is greater than 0, then we also know the given series also converges. So again, to apply the limit comparison test, we now need to find the limit as n approaches infinity of a sub n divided by b sub n. We will let a sub n be the formula for the given series, and b sub n be the formula for the series we're comparing to. So again, we start with the limit as n approaches infinity of a sub n divided by b sub n, and now let's change this quotient into a product by multiplying by the reciprocal of 1 divided by n cubed, which is n cubed divided by 1. Now multiplying, we have the limit as n approaches infinity of n to the fourth plus 3n cubed divided by the fourth power of n plus 1. Again, if we expanded the fourth power of n plus 1, the first and highest degree term would be n to the fourth. Because the degree of the numerator and denominator are both 4, the limit is equal to the ratio of the leading coefficients, which would be 1 divided by 1 or 1, which is greater than 0. And again, because we compare to a converging series, and the limit L is equal to 1, which is greater than 0, we know the given series converges by the limit comparison test. I hope you found this helpful.